Hello, I'm Bas Erikshoven and I'm also going to say a bit about the category of R modules. And in this little movie, the subject is morphisms of R modules. So Arno has told you what left and right R modules are, and now we're going to make a category of them, things like that. So we have to come up with what the morphisms are. So for details, I also give you a reference. For details, see Taalman's notes. They are available on the website of this course. Taalman's notes. I think they are called modules and categories. Categories, and then that must be chapter 1. The very first chapter of that text has these things. Okay, so we'll start right away. Definition. Let R be in the category of rings. So R is a ring, not necessarily commutative, and let M and N left R modules then a morphism from M to N is a map F from M to N, and this has to satisfy such that a few properties that are exactly the same as what linear maps have to satisfy for vector spaces. So Arno has already said that the definition of a module over a ring is very much like the definition of a vector space over a field, and for morphisms we can copy the same procedure. So the first property is that for every M1, M2 in M, we should have that F of M1 plus M2. So this is the addition in M here, and these are mapped to elements in the module N, and there we have the addition of N, and for that addition we have to have this identity. So this, in words, this means that F is an additive map. And also with respect to the multiplication by elements of R, we have to have a compatibility. So for every R in R, for every M in M, we should have that F of R times M, and this is the multiplication for the module M. This should be equal to first mapping, well, what you get when you first map your element to the other module, and then multiply by the same ring element. So these two conditions are what it means that a map is called a morphism of R modules. Okay, so let me make this little remark still. If R is a field, it is too high for me, then the linear map, these morphisms are exactly the linear maps, right? So that is so at least one example you are familiar with. And we are going to use categorical notation for this. So if we are going to make a category of R modules, then we should have, for the set of morphisms, we will call it hom R M N will be the set of morphisms F from M to N. That's the hom set. Well, what else do we need for a category? We need a few things like identity morphisms. Well, I think identity morphisms are given by the identity maps, we also need composition. So I'm going to formulate a little proposition that does this. So let R be a ring, let R in a ring, and we take for M, N, and P. Now we have 3 R modules. And for F from M to N and G from N to P, morphisms of R modules the composition G compose F, and this goes from M to P, is an R is a morphism of R modules. Is a morphism, so that is this. And let me say a bit more in the proposition for M, an R module. Let identity M is a morphism from M to M. And now I have all I need to be able to say that we have a category. So this gives the category of R modules, and we will denote it by notation R mod. Okay. So we have, well, of course a proposition has to be proved, but that is left as an exercise for you. It is not a difficult thing. You just have to check that if F and G satisfies these 2 conditions, then the composition does it too. But you can just expand all the formulas and there is nothing surprising there. Okay. So, well, we have heard that there are left and right modules, so let me just say that it is similar for right modules, right R modules, and so that also gives a category, and that gives us the category, let us call it R, okay? So we have now a category of left modules, we have a categories of right R modules. Okay, so, well, let me make a remark. As soon as we have a category, we can use the categorical language and the principles. So when we have a category, we can say what the isomorphisms are. And in the previous examples by Stefan, in many categories, he said what are the isomorphisms. And let me do it here too. Here, there is nothing surprising. So in our mod, we have the notion of isomorphism, because we have it in any category. F from M to N, a morphism, is an isomorphism if and only if there exists a G from N to M, a morphism such that G composed F is identity on M and F composed G is the identity on N. And so that is the right way to get to the notion of isomorphism, and then you can prove, one shows, a morphism F from M to N is an isomorphism if and only if it is bijective. So if and only if it is an isomorphism in the category of sets, right? And the only thing that you have to show for this is that, well, one direction is clear, I think. This direction, if it is an isomorphism in this sense, then there is an inverse map that is even a morphism of rings. This is clear. F has an inverse. Well, you could say G is an inverse, well, the inverse then, right? Of F, so F is bijective. And in this direction, you have to show that, so now we know F is a bijective morphism, and you have to show that the inverse must show that F inverse from M to M is a morphism. And that works, I leave that as an exercise to you. You have probably done such exercises for rings and for groups, and you do the same tricks. Or not trick, it is not so difficult. So we have isomorphisms. Then, well, before we go to examples, I want to say a few generalities about the set of morphisms between objects, between R modules. It turns out that these sets have more structure than just sets. So, as Arno has shown, well, how should I say this? Okay, let M and be R modules. Then we have this set, right? Home R mod M N, right? We have this set. And we want, this has extra structure. For one, we can add, so for F, if you have F and G, two elements in it, this gives us an element that we call F plus G, and it is pointwise addition, just as in the case where M and N were abelian groups. So F plus G should go from M to N, and just as it's pointwise addition, so M goes to F of M plus G of M. This defines F plus G. I mean, the claim is if F and G are morphisms, then F plus G is also a morphism. It's unfortunate that I erased the conditions, but to do this, you check that if F and G are morphisms, then satisfy the two conditions, and F plus G also satisfies them. But okay, that is a lot to write down, so I leave it again to the spectator. So this, yeah, they are. Yeah, and so the claim is also claim. This makes home R mod Mn into an abelian group. So there must be a zero element. Well, that is the element that sends everything to zero. And for every f, there must be an opposite, an additive inverse, and that is the one that you can guess it, right? You have to send m to minus f of m, and that will be your inverse. And then it is an abelian group. And if you don't know anything more about R, then this is the only structure I know. But if R happens to be commutative, you can do a bit more. So now assume, let me do that here. let us look at the case that R is commutative. So you know that when you do linear algebra, that the set of linear maps between two vector spaces is itself also a vector space. So you do not only have addition on it, but you can also multiply by elements of the field. And that doesn't use so much of the field axioms, it just uses that your field is a commutative ring. So now, assume R commutative, then for R in R and F in hom R mod Mn, we let R times F from M to N be the map that sends M to R times F of M. So this makes sense, right? F of M is an element here, and I can multiply it. N is an R module, I can multiply by R, and I get R times F of M. And I claim that this is a claim. This is a morphism of R modules. But now it is a bit interesting, a little bit, to look why, because it shows somewhere we should use the commutativity of the ring, right? So, so for all M1, M2, and M, I have to check that R times F of M1 plus M2 is what it should be. Well, if I work this out, it is R times F of, so when I evaluate it on M, I have to take R times that, so this is R times F of M1 plus M2, and because F is additive, this is R times F of M1 plus F of M2, where I put some parentheses, and then the distributivity will give me R times F of M1 plus R times F of M2. Okay, and this, by the definition of R times F, is R times F of M1 plus R times F of M2. So that is okay. And here I have not used that R was commutative, because there was only one element of R. How could I have? But okay, for every R prime in R, and for every M in M, I also have to check something. I have to check that R times F of R prime M is what it should be. And now I have to take, well, I apply the definition of R times F, so this is R times the F of R prime M, right? And now I use that R prime, that F is a morphism, so this is R times R prime times F of M. And I should compare this with R prime times R times F of M, right? Because for R times F to be linear, to be an R module morphism, the R prime should come out like this. But this is R prime times R times F of M. And you see that these two things are in the other order. And they are equal because the ring is commutative, right here. That is why you have this. So, if the ring is commutative, then we have seen here that also we can multiply morphisms by elements of the ring and still have a ring, a module morphism. And then the statement we can make is that in fact this gives the home set, which was already an abelian group here, it becomes actually an R module. So proposition, this gives home R mod M and the structure of R module. Okay, so, okay. Yeah, well, that's nice. And one can even say a bit more about the category, but this is how much we can say about the R modules. About the home, even more. So why, if we have for R modules, say M, N, and P, we can also look if the composition map has some special property. We can do home R mod. Well, why don't I take shorter notation, right? R mod of M, N times R mod of N, P goes to R mod of M, P by sending an F, G to G composed F. And the claim is that if, so for, this is bilinear, this is Z bilinear, this composition map is Z bilinear, by which I mean that if you fix one of the variables, it is additive in the other one. Okay, I'm not going to write it out, but and if R is commutative, even R bilinear. And this R bilinear stuff will play a role in the tensor products of the other lectures in this series. Okay, so we have that too. And then we can do, finally, examples. So, sorry for all the generalities. So now we can do examples. And so, well, we have already seen for K a field. In a field, we have seen vector spaces over K. Those are the, and then you have linear maps. So this is the same as the category of K modules, right? That's the same thing. And here, linear maps are, the linear maps here are the K module morphisms there. Okay. And we have a subcategory here, let's say vect K finite dimensional, FD, as Stefan denoted it, I think. And he showed that this was equivalent with the category with objects, with set of objects, the natural numbers, and with morphisms, if you want to go from n-dimensional to an m-dimensional, you take the matrices m times n, so m rows and n columns, with coefficients in K, and composition is multiplication. Composition is multiplication. And of course, you make the object n, what is the functor here that goes from this category to that? To n, you associate K to the n, and then it works by itself. Okay, that's one example, and this was already treated. Arno has talked about Z modules, so let's say this was the first type of example. Second type, modules over the ring Z is the same as abelian groups. every abelian group has a unique structure of a Z module, and that was the argument he gave. For every abelian group M, there exists a unique ring homomorphism from Z to the endomorphism group, the endomorphism ring of M. And this gives M a Z module structure, because a ring homomorphism does that. And then we can also in this category do a few examples. So, and here there are some new kind of modules that Arno also showed. I have a few minutes still. 5, huh?
4 minutes.
4. Okay, good. Let me do that. So here I want to look at I want to say something about this. Hom in the category of abelian groups of Z mod NZ to Z mod MZ. Right? That is now a kind of thing that we haven't seen yet. And I claim that this is, I map it to the set of X in Z mod MZ such that n times X is 0 in Z mod MZ. So that is, and how do I do that? If I have a morphism here, I send it to the image of the element 1 here. This is not only, well, 1 modulo n this is not only an abelian group, this is also a ring, it has a unit element. And if I know the image of 1, I also know the image of 2 and the image of 3 and the image of -1. So this map here is an injective map, right? It is injective because I only need to know f of 1 to know what the map was. Now I claim it's also, well, here is a condition on this n, because in this module n times this element 1 is 0, then it should also hold for this. Because f of n times 1 is n times f of 1, right? So here I have to get into these, and and now suppose I claim that this map is also surjective, because if I take an x here that satisfies this, well, if I take an x here, there is for sure a map from Z to that Z mod MZ, such that f of 1 is this x. So for x in Z mod MZ with n times x 0, I do have a homomorphism, say f from here. Yeah, there was a bit talk of initial object, right? Z is the initial object in the category of rings, and this module also happens to be a ring. So there is a unique f that is a morphism of rings here. And such, but I want not that. I want here that 1 goes to x, right? So forget that about the rings. 1 should go to x, but then as n times x is 0, then n times z here goes to 0 under this map. And so you know from your group theory course that then here you have a quotient map, and this map factors uniquely through a map through this quotient. And that shows that this is a surjectant. Then you can still analyze what is this set then. And the claim is that this is the elements in Z mod NZ, Z mod MZ, for which the GCD of n and m times x is 0. That is quite obvious, because n times that is 0, n times that is 0, then the GCD is also annihilating this. It is a linear combination of n and m. And
30 seconds.
Okay, 30 seconds. So what I want to say is that this is then m over GCD and m z modulo mz, and that is isomorphic by multiplication. Well, this is isomorphic to z modulo GCD and m z, isomorphic as an abelian group, right? Because the home sets are abelian groups, so it is this.